Hi, this is Mrs. Brown, and today we're going to look at factor the difference of squares. So if you recall from our special products lesson that when we had something like a plus b and a minus b, so this and this are the same and this are the same except one's plus and one's minus, the middle term is going to disappear. So we would end up with something like a squared minus b squared. Well, now we're going to go the other way. We have something like x squared minus 64, and now we're going to write it in this form. So if we take a look, one's going to be plus and one's going to be minus. And what we're going to do is look at x. Now, x squared is x times x, and this is the same as 8 squared, or 8 times 8. So we're taking the square root of each of these. This is x, this is 8, this is x, this is 8. They have to be the same number in order to make it work. If you look here, I have to take the square root of not just the variable, but the 4 as well. The square root of 4 is 2, and the square root of m squared is m. So if I'm going to write that, one's going to be plus, one's going to be minus. And then I take the square root of 100, which is 10. It may be helpful to you to just kind of list out some of the square roots. So 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, okay? And so on. That's 13, that's 14, that's 15, that's 16. By having some of these listed, and you only have to go so far, because I mean, you can use your calculator, but it may be easy reference to have these kind of listed out and to list, like having this as 1 squared, 2 squared, etc., so that when you're doing this, you have that information in front of you. That's your choice, whether or not you want to do that, but sometimes that can be really helpful just to have that as an easy reference. Okay. So let's look at some more examples. Let's say I have n squared minus 121. So again, when I look at that, the square root of n is going to be n. I'm sorry, the square root of n squared is n. Minus the square root of 121 is 11. And then it's n plus 11. Now, it doesn't matter which binomial I write first. I could also write this as n plus 11 and n minus 11. They're equally correct because remember, it's this times this. So the commutative property of multiplication says it doesn't matter which order it is. So it doesn't matter which one I write first. Okay. If I have 196 minus c squared, okay, 196, the square root is 14. It's listed first, so I'm listing it first here instead of the variable. One's going to be plus, one's going to be minus. The square root of c squared is c. Okay. 49m squared minus n squared. Okay. Again, I'm going to do the same process. The square root of 49 is 7, and the square root of m squared is m. Okay. The square root of n is squared is n. So 7m minus n. So again, you have to take the square root of the coefficient and the variable in order to make this work. Oops. Well, I just dropped my marker, so I guess we're switching colors. Okay. So if we take a look at the next one, sometimes you have to do a little work before you can do that. So for instance here, this isn't an x squared, it's x to the third, but you notice there's also an x here. So I have to factor out the GCF first. There's GCF of the coefficients is 1, so I don't have to do anything there. But between x to the third and x, I can take out an x. So I end up with 9x squared, because x to the third divided by x is x squared, minus 25. Now these are both perfect squares, so I can then go on to do square root of 9 is 3. And the square root of x squared is x, minus the square root of 25 is 5. And then I would have 3x plus 5. Okay. So sometimes you have to take the GCF first before you can actually rewrite it as the difference here. Okay. All right, let's take a look at another example. 36y to the third minus 4y. Okay, again, as I'm looking, I have a y to the third. I need like a y squared. So, or like a y to the fourth, that would be fine. So I have to factor it out, okay? Between 36 and 4 goes into 36, so it's part of the GCF. Y to the third and y would have a common factor of y. So I'm going to take out that GCF. So again, that means I'm dividing each of these by 4y. So you get 36 divided by 4 is 9, and y to the third divided by y is y squared. 4y divided by 4y is 1. And remember, 1 is a perfect square because it's 1 times 1. Now that I have my GCF out, I have two perfect squares. When I look at this one, the square root of 9 is 3 because 3 times 3 is 9. And the square root of y squared is y. And the square root of 1 is 1. Okay, and the same thing, but with a plus sign. Okay, let's look at one more of those examples. Okay, where we have to factor out the GCF. Okay, I don't have variables to deal with, but I do have numbers. The number that goes into both of those would be 3. So if I divide by 3 and I divide by 3, 12 divided by 3 is 4, so it's 4x squared minus 9. I now have perfect squares, so I can take the square root of 4, which is 2, and the square root of x squared is x, and the square root of 9 is 3. So 2x minus 3 and 2x plus 3. Okay. We're going to look at another type of problem. Let's say I have something that's a little bit more complicated, like x to the fourth minus 81. Okay. Now, x to the fourth is equal to x squared times x squared. So it is actually a perfect square, because if we use the product rule, 2 plus 2 is 4. Okay. So the square root of x to the fourth is actually x squared. Okay. So that actually is a perfect square, and 81 is a perfect square because you know that's 9 times 9. So I start by doing x squared plus 9 and x squared minus 9, except these are perfect squares. This is a plus sign. I can't do anything, but since this is a difference of squares, I actually can factor the second binomial into x minus 3 and x plus 3. Again, I can't do this one because this is a plus sign and I need a difference of squares. But since this is a difference of squares, I can actually factor that again after the first time. Okay, so let's take a look at another example. Okay. Okay. Again, just like x to the fourth was x squared, the square root, m to the fourth is the same as m squared times m squared, so it's a perfect square. 16 is a perfect square because it's 4 times 4. So I can go ahead and factor that into 4 minus m squared and 4 plus m squared. Now, this is a plus sign. I can do nothing. These are both perfect squares, so I can factor again. The square root of 4 is 2, so it's 2 minus m, because m squared, the square root will be m. And then 2 plus m, and I still have my 4 plus m squared. And again, I couldn't do anything with it because it was a plus sign instead of a minus, and it has to be a difference. All right, I'm going to look at one more example, and then we're going to look at solving an equation. All right. So if I look at this problem, the first thing you should notice is I don't have perfect squares. So that should be a clue to you that, hey, maybe you need to factor out the GCF. So between 3 and 27, 3 goes into both of them, and y to the fifth and y, you can remove y. Okay. 3 divided by 3 is 1, and y to the fifth divided by y is y to the fourth, minus, okay, and 3 goes into 27 9 times, and y divided by y is 1, and 1 times anything is anything, so it's just 9. Now I have two perfect squares, so I'm going to use my rule. Okay, y to the fourth is the same as y squared minus 3 and y squared plus 3. Now, this 3, not a perfect square. So I can't do anything else. I can't break it up like I did on the last 2 problems because this is not a perfect square. So this is, in fact, the final answer because I can't do anything else with it. Okay? All right, so last step is I want to look at solving an equation. So y equals x squared minus 4/9. Don't freak out because there's a fraction. Okay? So when y equals 0, what is x? So remember that with the other quadratics, again, we were making them equal to 0. We're going to do the same thing here. Okay, these are both perfect squares because the numerator and the denominator are both perfect squares. So I take the square root of the numerator, square root of the denominator. So when I'm looking at this, that would be x plus, okay, the square root of 4 is 2, the square root of 9 is 3, and x minus 2/3. So if I want to tell you what the answers are, the roots, I just make each of those equal to 0. So I end up, when I subtract 2/3, getting x equals to negative 2/3. And over here, when I add 2/3, I get x is positive 2/3. So the roots, or the answers to this equation, would be negative 2/3 and positive 2/3. So even when I have a fraction, I can take the numerator and denominator separately when I'm taking the square root. If they're both perfect squares, it works exactly the same as if it was with whole numbers. Okay? I hope this helps. Have a fabulous day, and I will talk to you soon.